Hi everyone. In today's lecture, we will see some graphs of functions and well, translations of functions and stuff. By translation, I mean there are horizontal translation and vertical translation, and also we have reflections of graphs. So before we go to that, we need to a little bit be familiarized with this basic functions or graphs of functions. For example, if we have a linear function, we have seen what a linear function is, and we have seen what a constant function is. So for a linear function, it's always a straight line, like this one. And a constant function, again, is a straight line, but in this case, it's a horizontal line, okay? So constant function, the graph of a constant function is always a horizontal line. And another function is, of course, this identity. Identity means the value of, for every value, or the value of y and the value of x are always the same. So as you can see, it's 45 degrees. I mean, if you look at this, it divides this one into two equal half planes. Therefore, this is called the identity function. And then we have the square root function, which looks like this one. We have the cube root function. We have the x squared function, y equals to x squared, and this is parabola. And we have the x cubed, which looks like this. And then we have the absolute value function, which is this one. And then the reciprocal, or 1 over x. And in this case, we have two separate graphs. And as you can see, both of them, they don't touch the y-axis. And in this case, this y-axis, we call it a vertical asymptote. Vertical asymptote, which means the graph gets closer and closer and closer to the line, but it never touches it. This is what we call an asymptote, okay? It's not always vertical. Sometimes, of course, even in here, we have the x axis. So the x-axis again is a vertical asymptote, and the y-axis is the x is horizontal, and the y-axis is a vertical asymptote in this case. So here, these are the basic functions and their respective graphs. And instead of memorizing always, when you have, or when you are given a function, for example, if you have f of x equals to x cubed, so instead of memorizing the graph, the best way to do this is to graph it yourself. And to graph it, we just use this technique. Okay, we pick random values of x, or arbitrary values of x, which always in which we always pick the smaller values around 0 on the negative side and on the x positive side. So that's the trick, is because when you substitute it in here, it's easy to evaluate it. So by preparing this table, we can always graph of a function. Okay, so by doing so, we can familiarize ourselves with these different functions or graphs of functions. All right. Now, given these basic functions, okay, we will see different types of translations of graphs. Now let's start with the vertical one. A vertical translation means when I have a graph, let's say if we have a parabola like this one, then we can take it a bit above that one, or we can put it down, okay? So this is what we call the vertical translation, okay? From the original place, we're taking it up or down. Now, let's consider this function. We have a function which is given by y equals to f of x, and suppose k is a positive real number. Now, the graph of f of x, the original function, f of x plus k, is the graph of the original function shifted k units to upward, okay? So if let's say you have the graph of this original function, to graph this one, you don't need to prepare a new table like this one, table of values. You just use this graph or the graph of this parent function, we call it the parent function, and then you shift it up by k units. So that means it's only shifted up by k units. Otherwise, the shape is the same. They have the same shape, okay? The shape doesn't change in this case. And if this is minus, if we have y equals to f of x minus k, then the shift becomes downward, which means we pull it down, we bring it down. And another type of shift is horizontal translation, or another type of translation is the horizontal translation of graphs. Again, here, let's take h, which is a real positive real number. And then we have, of course, our parent function is again the y equals to f of x. So the graph of f of x minus h, now notice the subtraction, or we are subtracting a value from x. In this case, we were subtracting value from f of x. First, you find value of f of x from the original function, and then you subtract k. But here, we are subtracting a value from x, okay? So if we have this f of x minus h, then the graph of this function will be shifted, will be the graph of the original function shifted h units to the right. Now this may get you may get confused in here, because since we have negative everyone, I mean, one would expect this one to go to the left, right? But this is the opposite. When you have minus inside, minus h, then the shift is to the right. But when it is plus, then the shift is to the left. Okay. Now let's consider some examples. Suppose we have this function, and I put the graph in here, the graph of the parent function, and we are asked to graph f of x equals to absolute value of x minus 2 plus 4. Okay, so inside the absolute value we have this one, and then we have plus 4. Now the question is, how can I use the translation techniques to graph this function? So in this case, there are two translations. One is vertical, this is vertical translation, and another is horizontal translation. Okay. Now, first, let's do this horizontal translation. So the horizontal translation, now, well, what is our parent function now? Our parent function is, let me use a different function, g of x equals to absolute value of x. Okay. So here we have the graph of the parent function. This is the graph of absolute value of x. Then to plot the graph of this one, well, what is now g of x minus 2? Okay. Now we need to plot the graph of this one, y equals to g of x minus 2. And what do we know? If we go back, this is what we have. If you have f of x minus h is the graph of this, then the graph of this function is the graph of this one shifted to the right by h units. Now our h is 2. So here we have h equals 2. Therefore, the shift will be to the right direction, okay, by 2 points or 2 units. Now, if we take this origin, then go 2 units to the right, so the new vertex will be at this point. Now, well, if you have a ruler, you can just draw a parallel line parallel to this one, and another one parallel to this one, which has the same shape. And if I can, I will try to make it as straight as possible. I guess this is okay. And the other one will be okay. So now this is g of let me see instead of calling it g, this graph is y equals to absolute value of x minus 2. Now we're doing this step by step. So first, what I did is I did the horizontal translation, which is this one. Now, as you can see, the original function or the graph of the original function is shifted to the right by 2 units. Every point on the original graph is shifted to the right. For example, if we take this one, this is shifted to the right here. If you take somewhere in here, this is at this point. So that's why I started with this, because this is unknown and it's easy to spot. So we shift the vertex and then we draw the line. Or if you want, you can take another point and shift it to the right 2 points, and another point, shift it to the right 2 points, and then you can connect the points. Now the next step is we have the graph of this one. Then we need to add this 4. So our k is 2. Okay. So here we have, if we call, let's say, if we call this one h of x or something, then we have the graph of f of x equals to x minus 2 plus 4 is the graph of this function shifted up by 4 units. Now, if I shift this one up by 4 units, I have to count here 1, 2, 3, and 4. It's a bit, if I can. Okay. So here we have, it's not even. Okay, I think now it's close enough. So we have 1, 2, 3, 4. So the new vertex will be here, and then the graph becomes like this one. Okay. So somehow it looks like this one, okay? Maybe my lines are not a bit straight, but anyway, I hope you get the idea. So to do this through translation, we do it step by step. We did the horizontal first and then the vertical, and then we arrived here. So this graph of f of x equals to absolute value of x minus 2 plus 4. Okay. All right. And then the next is vertical and horizontal shrinking. Okay, so we did the shifting. We did the horizontal and vertical shifting. And then we can do horizontal and vertical shrinking. By this, I mean, when we have, for example, a value a greater than 0, And well, if a is greater than 0, it could be between 1 and between 0, or it can be greater than 1. Then if a is greater than 1, graph of y equals to a times f of x. Now we are multiplying it by a constant a. Is the graph of y equals to f of x stretched vertically by a factor of a. Okay, so if you multiply this function by a, then the new graph, or the graph of this function, will be the original graph stretched vertically by a factor a. Okay, but if a is between 0 and 1, let's say if this is 1/2 or something like that, then the graph becomes, the original graph shrunk vertically by a factor of a. Okay, well, it makes sense. If a is between 1 and between 0 and 1, then it shrinks. But if a is greater than 1, it stretches. How about if a is 1? Well, in that case, it doesn't change, because f of x times 1 is just f of x. Therefore, it will be just the original graph. Now, in this case, in both cases, that means if we multiply a number, the function by a, well, as what we are doing in here, since we are multiplying a times f of x, our new y, the original x doesn't change, the x doesn't change. Both of them, this one and this one, they are taking a value x, okay? But in this case, we are multiplying the output f of x by a. So our new y will be the previous y, which is in here, because this y is the same with f of x. So the old y times a. Therefore, the new coordinate, or the new points, let's say if the point xy is on the line or on the graph of f of x, then x comma a times y is on the graph of f of x. Okay, x comma ay will be in on the new graph, or on the graph of a times f of x. Okay, so use this transformation to graph f of x equals to 1/3 absolute value of x. Again, first we graph the parent function. This is our parent function, which means when I say parent functions, it should be one of the basic functions that we saw earlier at the beginning, right? So those are what we call the parent functions. We start with those ones, and then we do the transformation, either multiplication or vertical shift or horizontal shift or shrinking, stretching, whatever. All right. So this case is, well, in this case, a is 1/3, which is 0. We have this case, okay? And when that happens, or when we have this case, what do? Well, the new graph is the old graph shrunk vertically by a factor of a, okay? Therefore, we shrunk this by a factor of a vertically. Now, for example, if you take a point, well, this graph is a bit weird because it's not. I'm gonna make a new one because it doesn't look good. Okay. Oops. Okay. Now, let me upload the parent function, and that one is something like this. Something like this. Well, not perfect, but anyway, good enough to use it for this for demonstration, right? All right. So now, how do we shrink this one? So you take any some point. For example, if I take this point, if I take this point, and if I multiply, if I shrink this one, well, still it will be there, right? Because this y at this point, remember, if x comma y is in this parent function, then x comma ay is in the new function, in the new graph, right? So here we have 0, 0, and then 0, 0 will still be 0, 0. Okay, it doesn't change. Therefore, the new function, the new graph will still start, or it will have a vertex at this point. And then we have, let's say, for example, 1, 1. X is 1, y is 1. And what happens to this new graph? Well, the x doesn't change, but the y is changed to a times y. Our a is 1/3, so 1/3 times 1 is 1/3. Therefore, our new graph will be 1, maybe somewhere in here. Okay, and then let me take this one. This is 2, 2. If we have 2, 2, then this will be 2, 2/3, which means 2, 2/3 is somewhere in here. Maybe this is maybe a bit high. Yeah, should go a bit lower. Yeah. And then on the negative side, similar, we have -1, 1 will be -1, 1/3, and 2, 2/3, -2, 2/3, and so on. So if you connect this, you get something like this. Okay, and the other side. To look like this one. So I will call this one f of x equals to 1/3 absolute value of x. Okay, so this is the idea. Just based on the definition that we have, or the explanation that we have, we can always plot the graph of a function by just using this translation. And this is f of x, y equals to absolute value of x. This is the parent function. All right. And then we have the horizontal shrinking and stretching of graphs. And again, we have a, which is a real positive number. Now, if a is greater than 1, then the graph of f of ax is graph of y equals to f of x shrunk horizontally by a factor of 1/a. Now, this is a bit, probably a bit confusing at the beginning, probably, but it's not that difficult again if you understand this one well. So we have y equals to f of a times x, and the graph of this function is the original function, the graph of the original or the parent function shrunk horizontally by 1/a. Okay, so here it's shrinking horizontally. And if a is between 0 and 1, then the graph is the original graph stretched horizontally by a factor of 1/a. Okay, so if it is between 0 and 1, it's stretching by 1/a. If it is between greater than 1, it's shrinking by 1/a horizontally. Now here, again, this is very important. This will help you. This can help you. Earlier we said x comma a times y will be on the graph of the new function, and in this case, x over a comma y will be on the graph of the new function given by this one. Okay, so you can use this idea if these are kind of confusing. You can use this so that you can easily spot what the new values will be. You can pick like few of them and then you can connect them, right? Okay, now let's look at this one. Suppose we have y equals to, well, I have to, well, this one doesn't have a function, so mirror this one, and oh, yeah, let me use it for this one. Yeah. Okay, so I have this, and this is g of x, g of x. This is y equals to g of x. Okay, so we don't know what the function is, but we have the graph of that function, and this is the graph of the function. Okay, and then we are asked to plot or to graph the function given by g times g of 1 over 2 times x. Okay, and what do we know about this? This is the, well, our a is between 0 and 1, so we have the second case. And this second case says it's the new graph is stretched horizontally by a factor of 1 over a. So here a is 1/2. That means 1 over a is what? 2. So 1 over a is 2. So the stretch is horizontally 2 units. Okay. Therefore, let's consider this point. In this case, it's -3 is 0. Okay. And what did we say here? X over a comma y is on the graph, right? So in this case, my x is -3. Well, if we divide this by a, because our a is 1/2, therefore the new point will be 3 over 1/2 comma 0, and this is -6 comma 0, because when we take the reciprocal of this one, we get -6. And it's not well aligned. Okay, so -6 is, I think it's here, and then if I take this one, this is -1 comma -2, so that we only change the x value. Therefore, -1 over 1/2 becomes -2. Therefore, it will be -2 is here, and -2 comma -2, it will be here, and then the other one will be here, and then 6 will be right here. Okay, then we just connect these points, and we have the graph of the new function. Okay. Okay. And as you can see, this graph is stretched horizontally by 2 units. Okay, by 1 over a means 2 units. And that's what we have right here. Okay. And another important thing here is reflections across the x-axis and the y-axis. And this is another transformation. So when you have a graph, you can always reflect it on across the x-axis and the y-axis. For example, if you have something like this, you can reflect this one along the y-axis, which along the x-axis, I mean, which will look like this one. Or if you have a function, something like this one, you can reflect it along the x-axis, because along the y-axis, I mean. So you can use the y-axis as a mirror, and the image of this one becomes this one. Okay, so that's what we mean by reflection along x-axis and the y-axis. And the reflection says if we have a function y equals to f of x, then the graph of y equals to negative f of x is the original graph reflected across the x-axis. So if we just put negative f of x, if we put negative here, then it gets reflected along the x-axis. And if we take the negative inside, so that the new function becomes f of negative x, then the graph is the original graph reflected across the y-axis. Okay. Now let's consider these two functions. So here we have the identity function, which is y equals to x, or g of x equals to x. Now we're asked to graph y equals to negative g of x. And if we have this, if the negative is outside, then the reflection is along what? Along the x-axis, right? And if the negative is inside, the reflection becomes along the y-axis. So in this case, since the negative is outside, the reflection will be along the x-axis. Now, how do we reflect this one? Well, for example, if I consider from here to the right point, to the right side, then this part, if we reflect it across the x-axis, then it will look like something like this. Oops. Not like that. That's not a good one. I can. Anyway, so it will look like this one, and this one, if you reflect it along the x-axis, it will go up, and then we will have something like this one. Okay, so the reflection becomes this, and this is y equals to negative x. Okay, and similarly, if you try to plot y equals to g of negative x, this is the same with this one. Okay, even if you reflect this function along the y-axis, because the reflection of this one will be this one, and the reflection of this one will be this one. Okay, so in this case, both of them are the same, but that's not true for all for every function. It's just exceptional for this one. And now let's consider this function. We have the square root. Now don't get confused with this one, because this, from what we know, is the imaginary number I. But here we are on the left side of the origin, right? So on the left side, the values of x are negative, -1, -2, -3, -4, -5, -6, right? And then if you substitute one of these values in here, for example, -4, then it becomes +4. So this is not I anymore. So you don't have to worry about this negative here. it will still give you a real number, not an imaginary number. Okay, now the graph of square root of negative x looks like this one, and then we need to plot or to graph the function given by y equals negative f of x, which means negative square root of negative x. And if the negative is outside, we know the reflection is along the y-axis, along the x-axis, right? So how can we reflect this one along the x-axis? Well, it just goes on this side. Okay, it takes the same shape, but on the lower side of the x-axis. Okay, so this is what f of x equals to negative square root of negative x. And y equals to f of negative x, this has to be reflected along the x-axis, along the y-axis, right? So what do we get? This becomes like this one, and this is y equals use a different color. F of x equals to negative, no, it's not negative, it's square root of negative x, which is square root of x. So this is just this one, and the graph is like this. Okay, so as you can see, the reflection is very helpful as long as you understand the concept and as long as you get used to it. Is very helpful, because if you try to construct the table of values for every function to graph, then it will take a lot of time, right? But if you understand these translations, once you have the basic functions or the graph of the basic functions, then you can just translate that function or that graph. Okay, that way it saves time and it's much more easier. And when we go higher in the mathematical or in the mathematics courses, then this will be very helpful. So it's good to really understand this topic. So here is the summary. I just copied this one from the book, and it will help you to memorize or to look at, because this is a summary of the whole section. So what is vertical translation, or how do we translate vertically, horizontally, vertical stretch and shrink, and horizontal stretch and shrink, and reflection, and so on. Okay, so for each case we have this table summarized in this table, and I believe this will help you a lot. So you can either pause this one and read it from here, or you can just go to your textbook, and of course you have it there. So this is just as a guide when you translate, when you make transformation, because in this example that we have been doing, more or less we did it just for one type of translation, each example separately, right? But sometimes you can be given one function that can consist all the translations: vertical translation, or vertical stretch or shrink, horizontal stretch or shrink, and so on and so forth. Okay, or even reflections. So to do so, like if it's that complicated, what you could do is first you can do the horizontal translation, okay, which is shift, and then horizontal and vertical stretch and shrink, and then reflection across the x-axis, and then y-axis, and y-axis of course, and then finally the vertical translation or shift. Okay, so this is just a guide for you to help you to construct the new, or to graph the new graph, or the graph of the new function. Okay, all right, so I hope this you understand this one. If not, please feel free to contact me to ask questions, and either by email or during the office hours, or well, if you need to meet, if the office hours doesn't work for you, we can even meet outside that one. Just let me know, send me email up. Okay. All right. So see you in the next lecture.